Okay, this is part two of the chapter 8 discussion, and we're going to talk about rotational inertia. Uh, an object rotating about an axis tends to remain rotating about the same axis at the same rotational speed unless acted on by an external influence. Almost sounds like Newton's uh, first law. Uh, the property of an object to resist changes in its rotational state of motion is called rotational inertia. And the symbol is I, capital letter I. Looks like an L, but it's a capital letter I, rotational inertia. Uh, the more mass if something that's rotating, the more mass it has towards the outer edge, the more rotational inertia it has. If all the mass is concentrated towards the center, it has less rotational inertia. So you can see here the masses that are spread far apart, they're difficult to rotate. Whereas if the masses are in close, it's easy. Let's see what the text says. It depends upon the mass of the object and the distribution of mass around the axis of rotation. The greater the distance between an object's mass concentration and the axis, the greater the rotational inertia. So it's a matter of they're both going to weigh the same, but it's how that mass is distributed that makes a big difference. Yeah, I'll demonstrate that when we come to torque. Okay. Okay, rotational inertia. The greater the rotational inertia, the harder it is to change its rotational state. The tightrope walker carries a long pole that has a high rotational inertia, so it does not easily rotate. It keeps the tightrope walker stable. So he's got this long bar. The bar tends to want to stay in put and doesn't want to rotate, so it gives him some stability. Okay. The same object has different rotational inertia depending on where the axis of rotation is. So you can see this pencil, if you rotate it around this axis, it's one rotation. If you rotate it about this axis, it's a different rotational inertia. And if you do it around the end, it's a completely different rotational inertia. You can see here, it's pretty well distributed, and this would be distributed. This would be easy to turn. This would be easy to turn. This would be a little more difficult because the mass is more towards the outer edge of the rotation. It's easier to rotate a pencil around its own axis, harder to rotate it around an axis perpendicular to its own axis, and it's hardest to rotate it around a perpendicular axis passing through an end. Okay, now these are some rotational inertias. It depends on the shape of an object and its rotational axis. I don't have anything to demonstrate it, but there's some videos where they will roll a disc and a hoop of the same mass and the same diameter. The disc will always win because the hoop has more rotational inertia than the disc. They don't really show a disc unless you take this one here, the solid cylinder, and squash it to where it's a disc and not a cylinder. So you can see that it depends on the weight distribution, what the rotational inertia is. Okay, you don't have to commit those to memory or anything. If I give it to you on a homework or a quiz, I'll provide you with the necessary formula for the rotational inertia. Okay, here's the demonstration. I probably gave you the answer before. A hoop and a disc with the same mass and the same radius are released from the top of an incline at the same time. Which one will reach the bottom first? Well, I already gave it to you. The disc will reach it first. Why? Because the hoop has more rotational inertia. Its mass is more towards the outer edge. It's distributed towards the outer edge of the hoop. So the disc will reach the bottom first. The hoop has larger rotational inertia. Okay, and that's the end of part 2